Okay, this is matrix multiplication, and we're going to get into matrix algebra today. Matrix multiplication. One of the keys to matrix multiplication is, so this one says a teacher gives a three-part test to her students. The correct answer on the first part is awarded 1 point, second part 1.5, and 2 points for the third part. The number of correct questions answered by 4 students is shown in the table below. Determine which student earned the highest combined score on their state test. Now you can just 18 plus 3 plus 8. I can do it this way. Or it could be done more efficiently with matrix multiplication. And this is a 4 by 3. I would need to multiply by a 3 by 1. One of the keys to matrix multiplication is that these inside ones match, and your result will be a 4 by 1. So that was 18 plus 3 plus 8, 29. My resultant is the outside ones when I do matrix multiplication. So they end up with student D having the highest score. So here they're showing matrix multiplication. So it's row times column. You got this row times this column. So 18 times 1 plus 2 times 1.5 plus 4 times 2.5. If I had a second column in this, it would become row 1 times column 2 gives me that spot.
Okay. So if you were to write out the 4 by 3, and then you were just doing multiply by ones, multiply by the 1.5s.
So, yeah, you can see that row times column, it's all added together to give me, so if it's row 1, column 1, I get resultant space 1, 1. Row 2, again, column 1. Row 1, column 2 gives me this single space, which, yes, it looks all long written out, but it's a single number because we multiply and add. I'll go through an example.
Writing something down there.
This is easier to learn in examples. Um, we'll come back to that. So let's actually multiply these.
X.
1 times x plus x times 3, yes. So my matrix becomes 4x.
Wait.
3 times x plus 7 times 3.
Why is it not a 2 by 2 matrix in the end?
So I have a 2 by 2 multiplied by a 2 by 1. These match, so I can multiply. My result is that. So I cannot actually multiply BA.
Oh,
Because they don't matter.
Two bits.
Matrix multiplication is not commutative. How about down there?
Here?
Yeah.
No, I remember this rule.
Yeah. It's like it's kind of nice because you've done this before. So, given this, find the value of A and B, and well, we're going to find all three of them. I don't care that they didn't ask for them all. So, row 1 times column 1. X squared plus 6y equals A. So when I multiply, does that make sense? So I'm going to multiply these two and get that. Okay. Row 2 times column 1 should equal that spot.
6.
Okay, so row 1, x squared times 1 plus 2y times 3. Row 1 times column 1. Now I'm doing row 2 times column 2. 1 times y plus 2 times 3 equals 4. Well, that's nice. Y equals -2. That's helpful. Next multiplication, 1 times 1 plus 3 times x equals c. I don't know what x is yet. So this is column 1 of my matrix. Now I'm on to column 2, and I go row 1 times column 2. 5x squared plus 14y equals b. 5y plus 14 equals 4. And that is true. If I plug in -2. 5 plus 7x equals 33. X equals 4. So I have not found what they asked for yet. They asked for A.
X, Y.
I have X and Y, so I can get A.
A.
Yes, I have 16 minus 12 equals A. A equals 4.
So you just gotta like plug those in until you see
Mhm.
it again.
And I did all my multiplication. A equals 4. I can plug in and get B here if I wanted. I can plug in and get C. Yeah. And yes, I don't like writing this in the matrix form. I like writing it in these equation forms. I think it just was simpler. Okay. In 1 month, factory A produces 452 wallets and shipped 270 of them. Factory B produced 720 and shipped 514 of them in the same amount of time. Write a 2x2 matrix to represent this information where each row represents one of the factories. $270. So that's the rows represent a factory. 720 times 514. It costs each factory $12.74 to produce one wallet and 279 to ship it. Right, a matrix that represents the amount of money spent by each factory on production in 1 month. So I need to multiply these by that, right?
Escape. Question mark.
No, this row by this, the second row by that.
Oh, so basically multiplying it a 2 by 2 by
2 by 1. 74, that's a 4. So then my equals matrix is going to be 452.
And this is going to be like a total cost.
This is going to be a total cost for each factory. 452 times 1274 plus, so row 1 times column 2, 270 times 239. Do you have a calculator? And then 720 times 1274 plus 514 times 239.
70.
Yes.
Is it 2.39?
It's 2.39, yes.
The first one I have 6,000 oracles. 0.78. I don't know if we. I guess
No.
it's 05.
Usually you're going to two significant digits. Round your answer. Oh, it says to the nearest cent.
So then that would be 0.8. Nearest cent.
Mm-hmm.
0.78 then.
I was doing three significant figures, but you're not supposed to. 6, 4, what? Oh, 3,
70.
7, 8. This one was 1,401. So my calculator did not show enough digits when I did this. So what I did was I hit answer times, I just hit times 2. And then when it shows answer, it's going to show extra digits. Because mine only said 0.3 because it rounded it to 6 digits.
So it gave you.
Well, it gave me the answer, but all I'm doing is looking at the answer that it used. So it didn't actually give me this.
Extra, yeah.
So I just did times something. I suppose I could have done times 1, but I have to actually look at it. Will give me in the computation line more decimal places than it shows in the answer. Okay, now on to matrix algebra. Matrix algebra is where this starts to get. Matrix multiplication is just tedious and you have to be careful. Matrix algebra is where this is going to get a little bit harder. You have the zero matrix, which is exactly what you would think it is, all zeros. The identity matrix looks like a 1 down the diagonal. The identity matrix is going to be capital I. Okay. An identity means when I multiply by it, nothing changes. Noah, wake up. All identity matrices are what we call square matrices, where rows and columns are the same amount. Notice negating the matrix was pretty simple. You just negate every term. Any questions on that so far? So this is pretty basic stuff, but A plus zero, A plus a matrix plus the zero matrix is the matrix. The identity matrix,
And zero matrix.
yes. A plus negative I equals the zero matrix. I think they're kind of using an O for that. A times the zero matrix is zero. These should be pretty obvious. Adding zero to something doesn't change it.
Yeah.
Multiplying by the identity matrix, and you can do these in either order because they're both square. You can't multiply a 2 by 3, but I guess can you multiply a 2 by 3?
Seems always square as well.
Yes.
They're all square.
Well, it doesn't have to be, I guess. The identity matrix does have to be. This has to be 3 by 3. It's not really, we don't really multiply identity matrices by anything that's not a square matrix. So A pretty much has to be a square matrix for this. The zero matrix squared is still zero.
So, cause like I thought order mattered, so why are we able to switch the order with the zero as the identity matrices?
Okay, so order does matter. Why can you switch the order? So this, you can switch the order
Anything?
because of all the zeros. Okay. And you can change the order because you're only doing square matrices.
So yeah, you can only change the order if it's a 3 by 3 times 3 by 3.
And you only do these things to square matrices. That's why you can change the order. Yeah, okay. Okay, so this an expanded form. This is a little weird. You cannot use the shortcuts on this. A plus B times A plus B, and these are matrices with the capital letters. A squared. No. Plus AB plus BA.
Oh,
Order matters. Yeah, you can't do the 2AB.
dang.
Uh-huh. So this one is 3i times 3i is 9i squared. Three I times A is 3IA. A times 3i plus A squared. Now we will simplify this. The identity times the identity is just the identity. It's like 1 times 1 is 1. Now it is important though that I still have this I because it's not 9, if it's say it's a 3 by 3, it's 9. Does that make sense? which means I could actually add it to another 3 by 3. You can't add a scalar to a matrix, but you can add this matrix to another matrix. I times A is really just A.
What, well. Oh, I see, because even if we went 3 times I, it would be the same as 3 times A.
Mhm.
Wait, would it though? Cause then, cause we'd have like a diagonal of threes if we went 3 times I.
Yeah, which means
But if
what
you
happens with
three-
these diagonals?
Everything by 3.
What happens with these diagonals is because I'll multiply row 1 times column 1, and it just multiplies 9 times the one value, plus 0 plus 0. And then I'll multiply row 2 times column 1, and I'll get 9 times the first value plus 0 plus 0. So it's really effectively just multiplying the same as by a scalar. So I'll do it with let me show it with a 2 by 2.
It's like, I'm not getting there. It's making sense.
Yeah, and then because they're both 3A's, I can make them 6A. So yeah, let's do something like this. A, B, C, D times an identity matrix. And it would work the same if it's 2. So I get A times 1 plus B times 0, which equals A. Then I do row 1 times column 2. A times 0 plus B times 1. Row 2 column 1. C times 1 plus B times 0. Row 2 times column 2. C times 0 plus B or D times 1. Let's bring this is away from before. So if these were 2's, I'd just have 2A. Just like I would with a scalar multiple.
It'll make sense when you write it out.
Yeah, you really do have to write things out to justify stuff.
Okay, this one down here. The A times 3I also just simplifies to 3A.
The 3A, and then 3A plus 3A can simplify to 6A.
And then the A squared is the same.
A squared I can't do anything with. So given this, we're supposed to show that this equals the 0 matrix. So that equals that.
Well, we can, if we just divide both, so, actually.
You can't do matrix division. There is no matrix division. But A is equal to A times I, correct? Notice I did put it on the right side. So that means B plus C has to equal I.
Do matrix division.
Well, I can justify. So if something times something else equals something times something else, the something else's have to be the same. I can justify this with inverses later, but
No.
So this becomes I minus I, which is 0, right?
Yes.
And then A times the 0 matrix equals the 0 matrix or the O matrix. And it's not uncommon for us to oh, okay, I see what they did. They did it a different way. They distributed and subtracted A from both sides. And then A is equal to A times I.
You get to 0 on the row on the one side.
That's another way, and then you factored out the A. That also works. I was going to do, I can show you inverse matrix here in a second. So, determinant of a matrix. You only have to do determinant of 2 by 2. And I think I did introduce this to you.
It's continuous.
Yes, A, B, C, D. Determinant of A is equal to AD minus BC. The determinant has several properties that will get used later in this course. The inverse matrix looks like this. We don't divide by matrices, we can multiply by the inverse, though. You can inverse however much you want on your calculator, but you will not inverse anything more than a 2 by 2 by hand. Other useful things, this stands for determinant.
Well, like A thing.
The like absolute value box.
Symbol for so many. It's
I don't know why you
absolute value. What did we
It-
literally just learn the other day? Hold on. With the modulus.
Which, oh yeah, I really only use it for I would write it as det A. I only use that notation for
Use it for magnitude.
I use it for magnitude, which kind of makes some sense.
It's for uniright.
I was like, it makes sense on that one. It's because it's very similar to absolute value of magnitudes are always positive. So find the inverse of this matrix, and then we have to do the multiplication to confirm it, that it is actually an inverse.
Oh, it divides so we can multiply magnitudes.
Yes. Yes. Sure. So matrix multiplication with an inverse is commutative. So that is, this term is also important. Your calculator will show it, singular matrix. That means the determinant is 0, and you'd have 1 over 0, meaning you don't have an inverse. When you're doing the inverse, you have 1 over determinant. So if determinant is 0, you don't have an inverse.
0.
And that's called a singular matrix. Your calculator will show you that sometimes. So here I'm gonna to find A inverse. We first have to find the determinant. That's -2. It's -17. That makes sense so far?
Mhm.
That's right. Now I start switching the orders around. And yet my inverse matrix is actually so I'm distributing that through, which practically speaking is this, right? And it's only going to make us show this one direction with the multiplication, but here it now says multiply A times A inverse, and you should end up with the identity. So A So I've got 1 times 2/17, row 1 times plus 5 times 3/17. That's 2/17 plus is plus 15/17 is 1. 17/17. Row 1 times column 2. 1 times 5/17 plus 5 times -1/17. 5/17 plus -5/17 is 0. Row 2 times column 1. 3 times 2/17 plus -2 times 3/17. That's 6/17 minus 6/17. Row 2 times column 1. 3 times 5/17 plus -2 times -1/17. It's 15/17 minus 2/17 is 17/17 or 1.
So just like proving.
We're proving that it equals the identity. That's a very easy proof, actually.
So wait, to prove that it was equal to the identity, we
Just literally
found
multiplied it.
the inverse.
That was the first question was find the inverse.
So we found the inverse and then we multiplied it by the original
Mhm.
to prove that it
To-
really was the inverse.
To prove, yes.
Mhm.
You could prove that by doing this with AD minus BC.
And
Uh-huh. If you did this in general, that would prove that this is true all the time. All we did was show it in the specific case. Find values of x such that x is not a singular matrix. So singular matrix means the determinant's 0, correct? So I'm going to do the determinant AD minus BC. And I'm going to solve for x. So I'm going to find when it is equal 0. Everywhere else it's not. So 8 equals 2x squared. I'll divide by 2. 4 equals x squared. X equals plus or minus 2. If I did this in interval notation, it would be this. You can probably on this say anything x is anything but -2 and 2. I'm guessing that's how they wrote it here. X is not equal to plus or minus 2. IB is fine with that. I made you guys do interval notation and pre-calc to make you learn it. Well, I just put X as, that's what I just wrote out.
Uh, uh, how is that interval notation?
This is,
Oh, yeah, okay.
that's the same. IB will take you there.
Those are the values that make it
Work. Find the values where it's not a singular matrix. All of these values, which is kind of why I wanted to write that out.
Is there is no inverse.
There's no inverse because the determinant is 0.
0. Okay, so we put the equation for the determinant over there, and then we set it
Equal to 0 and solve,
solve.
found where it would equal 0.
Perfect.
Okay. Find the inverse of this. You are not to do that by hand. So you're going to put this into a calculator. I'm going to write it down so I can still see it when I switch to the calculator. Oops.
Do I go to my matrix now?
Yes, do your matrix button. This button here. Choose the one that looks like 3 by 3. Tell it 3. Oh, I could just hit, yeah, I just hit enter. You have to be careful scrolling through those that it doesn't change it.
We tried to use this calculator once.
That is the most frustrating part, that the arrow thing does both things. So this, on the 84, there's actually an inverse button. You can't just, on the Inspire, you just hit to the power of -1. And there's our inverse matrix. You will not be asked to do a 3 by 3 by hand. It is doable. It's a pain in the butt. Mostly it's just really tedious because you have to, the determinant involves finding determinants of these 4, well, these 4, I'll box the ones and then putting them together. And I don't remember exactly what the formula is, but it's these 4, and then you find the determinant these 4, and then those 4, and those 4, and then you combine them all somehow. And I don't remember how that is. But
The idea makes sense, but I don't know how you would execute it.
I don't remember. You don't have to know it for this course.
Squares makes sense.
And that applies to anything else. Okay, solve this for x. Well, we cannot divide by matrix A, but we can take AX equals B. I can multiply by the inverse, but I am left multiplying, which means I must left multiply there.
Okay. And then we have identity matrix
So this becomes IX.
equals A
Oops.
inverse of A times B.
IX. A inverse times B, which means X equals A inverse B. And that order matters. Show that your solution is consistent with orders B and X for any singular non-singular square matrix A. What is I don't remember what they mean by this. So, well, okay. They're just saying they all have to be A inverse for any. Oh, okay. They're saying that this doesn't have to be A is n by n if it has an inverse. X does not have to be so it's n by m.
A has to be square.
You can't inverse a non-square matrix.
Okay. So like that's a flaw. This is that it only works if A is square. We
Mhm.
don't know if A is square.
Well, it has to be if you're going to
It has to
inverse.
be. That's the only way to solve this is
Mhm.
what they're saying.
Yes. With the orders of B.
It's a non-singular square.
Mhm.
It is tell it well.
It does tell you that. And so AX, X has to be n by m. A inverse will be n by n. So A inverse times B would also have to produce an n by m, is all they're justifying there. Um, we're going to go through these last two and save us a little time tomorrow. So you're given that AB plus C equals D, and that matrices A, B, C, and D are 2 by 2. Solve the equation for A. I can subtract matrices from any side. They're all the same dimensions, so this will work. Now I will left multiply by A inverse. I do not want to right multiply because it'd have to be on the right side of the B. You cannot multiply in the middle. You can only multiply to one or the other side of the equation. That's left multiply. I don't remember what I said. I'm supposed to solve for A, not for B. Helps if you solve for the right matrix. So that means I'm going to right multiply by B inverse. So I get here A equals DC times B inverse. Has to be in that. Yeah.
That makes sense. It's pretty like simple.
Because the B inverse. You just have to get used to the left and right multiply.
Like if someone else would do this and they weren't square matrices though, like
You can't do it.
you just can't. Like you just can't do it.
Mhm.
You just can't multiply this.
And yeah, like everything Jackson did in his project was square matrices. So most applications end up using square matrices a lot. So this is really interesting. The inverse of A times B is B inverse A inverse.
I mean, it's like distributing it.
It's not distribute, it's got to switch the order though.
Oh,
And I'm going to prove that.
sad.
Yeah. So I'm going to show the proof. We'll see if I can remember how to do it without looking. It's actually not that bad. So AB inverse. I don't remember the first step. I know it's not the. Okay, so first step here. AB times AB inverse should equal I, correct? That makes sense?
Yes.
Now I will multiply both sides by A inverse.
Oh, it's because the order matters, like left to right.
because order matters. Yep.
Yep, and so then we're being your A switched.
So these become I, B.
In first. We don't really need the I in.
You don't really need the I.
And then
I don't need any of these I's.
we do B,
Hmm.
inverse.
And
Since we're left multiplying, we have to left multiply on the other side,
mhm,
and that's what switches them.
that's what switches the order. That's a really, it's not that hard. So as you look at these proofs, you don't have to prove something like this on the test. They'll occasionally have you like show that this works out with numbers. They don't have you do any formal proofs. They might say show.
And then that's what
Um,
this means.
Yeah. And they wouldn't have you do one. This is borderline formal proof. But understanding the proofs is how you get those higher scores.
Gives us a-
Your brother agreed. Vectors are a form of a matrix too. So
Since this,
they will.
speaking of trigonometry, yes, it'll make more sense.
And the second time through going through stuff really helps. Okay, so that is matrix. We're gonna do applications and this cryptography application tomorrow. So that's it for today.